All right, so welcome to the next unit. This unit is called energy, but it's also known as thermochemistry. So on this page here, there's a list of outcomes that students are expected to follow here. So make sure you just take a moment to pause and read through all of this. We will be covering each of these points in this note package. Okay, so getting started with some terms for thermochemistry here, we need to understand the difference between potential energy as well as kinetic energy. So potential energy is stored energy. So for much of our unit, it will be the stored energy in chemical bonds within as well as between molecules. Okay, so the bonds within molecules, those are called intramolecular bonds, whereas the bonds between molecules, those are called intermolecular bonds. So examples of intermolecular bonds would be like your London forces, dipole-dipole attractions, and hydrogen bonding. Examples of intramolecular bonds would be covalent and ionic bonds for that. So during a phase change, potential energy changes without a temperature change. Okay, and visually this is displayed as flat lines on heating and cooling curves. There's no heating and cooling curves below, so that's just a little error there. Okay, now kinetic energy is the energy of motion of ions, atoms, and molecules. So this could include translational, rotational, vibrational motion. Okay, and kinetic energy is temperature dependent. Okay, so the reason why we say it is temperature dependent is just because temperature is a measure of the average kinetic energy of molecules here. So when we get to calculations, the difference between potential energy and kinetic energy, like yes, potential energy is all about stored energy and kinetic energy is all about the energy of motion, but when it comes to calculations, where this is going to apply is potential energy, because it relates to stored energy, it's going to be talking about chemical reactions. Whereas kinetic energy is going to be talking about substances that don't necessarily undergo a chemical reaction, but it does undergo a temperature change. Okay. So thermochemistry is the study of heat or energy changes associated with physical, chemical, as well as nuclear processes. So some terms that you're gonna want to be aware of in this unit is heat. So heat is just a form of energy that flows between two samples at different temperatures, and heat always moves from hot to cold. Okay, temperature, as I said previously, is the average kinetic energy of molecules. So just as a reminder here, kinetic energy, that's all about the energy of motion. Okay, so temperature just measures the average motion of molecules in a sample here. Now it isn't going to reflect total energy, only the random movements of atoms and molecules. Thermal energy is going to be a measure of the total energy in a substance. Now heat and temperature are related. However, you got to keep in mind that they are two different things. So, for example, if something absorbs heat energy, the temperature increases. Okay, so except for during a phase change. That's where it's going to plateau a little bit. And then once the phase change is finished, then the temperature will keep on changing. Okay, so with this, you do got to understand that heat and temperature are two different things, and the more you heat something up, the more you're going to increase the temperature of it, so the higher the kinetic energy that substance is going to have. So let's write that right here. So higher temperature will give us a higher kinetic energy, which means that particles are moving more. So the second law of thermodynamics is going to keep on coming up in this unit. So what it is, or what it states, is that heat is spontaneously transferred from one object that's at a higher temperature to another object that's at a lower temperature until both reach the same temperature. Okay? So this is going to be something that keeps on coming up throughout this unit. So most substances are solid or liquids at room temperature. There's a few that are gases. Solids and liquids are called the condensed phase, so that's when you have your particles closer together. The attractive forces between molecules, so we're talking about the intermolecular attractions, such as London forces, dipole-dipole attractions, and hydrogen bonding. They are going to be what holds the molecules closely together. So our three phases of matter are the solid phase, liquid phase, and gas phase. So in the solid phase, that's where we're not going to have a lot of movement of molecules. Okay, and the reason why we don't have a lot of molecular movement is just because in a solid, the intermolecular attractions are very strong, which gives us our rigid structure of solids. Okay, there's only some back and forth movement, which is going to be vibrational motion, and the particles have very strong attractions and are very densely packed. Okay, in the liquid phase, there's enough kinetic energy to overcome some of the intermolecular attractions, resulting in loosely bonded flowing systems. And the particles are freer to move in any direction. So this is going to mean that these particles in a liquid phase have vibrational, rotational, and translational motion. And there's still strong attractions between particles, so particles are still densely packed. Now, in the gas phase, this is where we're going to have lots of movements of molecules. Now, gas molecules have so much kinetic energy that the intermolecular forces are overcome and become negligible. So basically what that's saying is the intermolecular forces don't really affect the particles. It's not holding them together. Okay, so this results in a completely random system. So what they mean by that is that the molecules are moving around so fast, and because they don't, or the intermolecular forces aren't very noticeable, the molecules are moving completely randomly. So molecules have a little bit of vibrational, rotational, and translational movement, but mostly it's translational motion. Because there are essentially no intermolecular attractions, particles are very far apart. All right. Getting into kinetic energy, so this is going to relate to the changes in intermolecular bonding. One term that we have to talk about is heat capacity, which eventually is going to go into specific heat capacity, which is something that we're going to be using in calculations. So the heat capacity of a substance is a measure of the energy required to raise that amount of substance by 1 degree Celsius. The units for heat capacities are joules per degree Celsius, and just like enthalpy, heat capacity will change depending on the amount of substance involved. So, for example, it will take more energy to heat up a bathtub full of water to 55 degrees rather than a cup of water at 55 degrees because you have less water in that cup. And just like enthalpy, we're going to standardize our heat capacity measurements so that they can be compared. So we have molar heat capacity, which is joules per mole degree Celsius, which allows us to see which substances require more or less energy to heat up or cool down because they all involve the same amount. Unlike enthalpy, specific heat capacity is used. So what that's saying is specific heat capacity is the most important one here. Is used because in industrial applications we want to know how quickly something might heat up or cool down, and we can more easily measure the mass of the substance than moles. Okay, so specific heat capacity, the variable that we use to represent it is a lowercase c, and it is the amount of heat needed to raise the temperature of 1 gram of a substance 1 degree Celsius. Okay, actually, there's a typo here. Or 1 degree Kelvin. So 1 degree Kelvin is not the same or not equivalent to 1 degree Celsius, so make sure that you cross that out. Now, the specific heat capacity is different for different substances as well as different states. And we're going to find a few of these specific heat capacities in your data booklet. So if we take a look here, it's going to be on page 3. So page 3, right near the top, we're given specific heat capacities at 298.15 Kelvin and 100 kilopascals. So 298.15 Kelvin, that's just 25 degrees Celsius. Okay, so the specific heat capacity for air is 1.01, same with polystyrene foam cup. Copper has 0.385 joules per gram degree Celsius, so on and so forth. And out of this list, we can see that water has the highest specific heat capacity, okay, at 4.19 joules per gram degree Celsius. So it's very important for you to know where to find all of these specific heat capacities, because most of the times you'll get questions where they'll mention what substance that you're using in your problem. However, they won't give you your specific heat capacity. You need to know where to look it up. So again, this is page 3 of your Chemistry 30 data booklet here. So looking at the data booklet, we can see that water can store more energy than air or aluminum. So looking back here, like I said, water has the highest specific heat capacity, whereas air is 1.01 and aluminum is 0.897. Okay, so what this is saying is that water can absorb more heat per gram before changing temperature, or before changing a degree Celsius, compared to air or aluminum. Okay? And you can kind of think about that, where it's faster to heat up some air or faster to heat up a piece of aluminum compared to amount of water. Okay, so what I just said goes over this point here. So because water can absorb quite a lot of heat before it itself changes temperature, that's what makes water a good coolant, just because it can store heat quite well. Okay, so because it takes a lot of energy to heat up an amount of water, that means it's also going to take a lot of energy loss before water lowers by 1 degree Celsius. Okay. Now this next point here says when 1 gram of aluminum goes up by 1 degree Celsius, it only absorbs, so we need to change this. This is going to be 0.897 joules of energy. Okay, and again, where we're getting this is from this right here, this specific heat capacity. Okay, but the reason why the units are different is because we're just talking about how much energy 1 gram of aluminum can absorb before it goes up 1 degree Celsius. Okay, so let's make sure we also change this to the correct specific, or the correct number. Okay, so when the temperature of aluminum drops by 1 degree Celsius, only 0.897 joules of energy is given up. This explains why you can touch aluminum foil that has just come out hot out of the oven. Okay. As well, a drop of boiling water on your skin is not going to destroy your skin tissue, so it's not going to transfer a whole lot of heat to your skin tissue because there's not a whole lot of mass to that drop of water. However, with a cup of hot water, because there's more mass, so it's holding more heat, that will scald your hand. So effectively what we're saying is the higher the specific heat capacity of a substance and the greater its mass, the more energy that it can store. So we're going to be calculating the heat transferred to or from a substance if we know the specific heat capacity, mass, and temperature change of the substance. So those are the 3 things that we need to know in order to be able to calculate heat transfer. All right, so we've been given this formula. Kinetic energy is equal to mass multiplied by specific heat capacity multiplied by the change in temperature. Okay, so very important to know or memorize this formula because it's not in the data booklet. Okay, so what do each of these variables mean and what units should they be in? So EK, that's just kinetic energy. It can be in joules or kilojoules. Mass of the substance, that's M, and then that's going to be in grams. C is for specific heat capacity. That's going to be in joules per gram degrees Celsius, and change in temperature is in degrees Celsius, where delta T is going to be expanded to the final temperature minus the initial temperature. So that's another formula that you need to memorize. So all of these variables, when you're doing your calculations, all of these refer to the same substance. Okay, so if you were trying to figure out the kinetic energy of water, okay, you would use the mass of water, the specific heat capacity of water, and the temperature change of water. Just as a heads up, for this formula, you may also see it as Q is equal to MC delta T, but just know that kinetic energy, EK, like both of these are the same formula. We're just using EK instead of Q. Okay, and that's just because it makes it a little bit easier to understand. All right, so kinetic energy is going to have a negative value when something loses heat, so temperature decreases. So this is going to be the sign that an exothermic process is happening when heat is being lost. So to help you remember the difference between exothermic and endothermic, you can think of exo sounds like exit, as in heat is exiting the system. So if heat's exiting the system, that's why it's going to be a negative value. Okay, now when I say the system, in chemistry, what systems are, like it could be anything, but in chemistry, a system is generally like where your reaction is taking place, okay? Or the vessel inside the vessel where your reaction's taking place. So just as a side note, let's just maybe right up here, because I don't have a lot of space. So a system could be anything. But in chemistry, a system is generally, so I said a reaction vessel, but a reaction vessel could be something like a beaker. So that's what I'm going to use. So a system is generally a beaker where your reaction's taking place. Typically. Not all the time, but that's typically what it's referring to. So a beaker, yeah, sure. Okay, so kinetic energy is going to be a negative value when your system is losing heat, and if your system is losing heat, it's going to be an exothermic reaction. Okay, Kinetic energy is going to have a positive value when your system is gaining heat, so your temperature is going to be increasing, and that's going to be your sign that you have an endothermic process happening. So for endo just means in or enter, kind of sounds like endo. That's how you can remember it. So the heat is entering the system. So if heat enters the system, your system is gaining energy, so that's why kinetic energy is positive. So I'm abbreviating kinetic energy to EK. Okay, so you do need to understand the difference between exothermic and endothermic processes, okay, and how heat is transferring either to or from the system. Okay, another important detail here that's going to be coming up later is that if you're ever given a volume of water, just remember that 1 milliliter of water is equal to 1 gram of water. Okay, so that is something that you need to memorize because it does come up throughout this booklet. All right, so first example here, we have a propane stove that heats up 150 grams of water from 20 degrees Celsius to 53.2 degrees Celsius. How much energy is required to heat the water? So because we're asked how much energy and a chemical reaction isn't happening, just a temperature change is happening, that's why we know that we are looking for kinetic energy. We were also given a mass of 150 grams, and we were given two temperatures. So the first one here, that's going to be our initial, and then the second one is going to be our final. So figuring out the temperature change, I'm going to go final minus initial. So 53.2 minus 20, that's going to give us 33.2 degrees Celsius. Okay, now the last thing that we weren't given, so we're asked for kinetic energy, we have mass, we have change in temperature, but we weren't given specific heat capacity. We need to look that up. So the identity of our substance is water. Let's look up the specific heat capacity of water. That's going to be 4.19 joules per gram degrees Celsius. So let's write that out. Okay, so whenever I'm doing calculations, I do like to write out a list of givens just to organize my information. And then the first step of actually calculating, I write out my formula. So EK is equal to mc delta T. So EK we don't know. Now we're at the point of we're substituting in values. So mass was 150 grams, specific heat, that was 4.19 joules per gram degree Celsius. And then change in temperature was 33.2 degrees Celsius. All right, so if we look at our units, notice that we have grams on top and grams on the bottom. So that means that they're going to cancel out. Okay, so basically if you have the exact same unit in the numerator and denominator, they cancel out. So degrees Celsius is in the top and the bottom, they cancel out as well. Okay, so let's multiply all of this together. So 150 times 4.19 times 33.2, and we get 20,866.2. Okay, and since the only unit that didn't cancel out is joules, that's what we're working with here. All right, so as a reminder, whenever you do a calculation in chemistry, you need to take into account significant digits. Okay, so what significant digits are is you got to look at the numbers that you were given in the question and figure out how many significant digits those have. And once you figure out those, they are going to determine how many significant digits your answer can be in. Okay, so effectively, you find the value with the least amount of significant digits, and however many significant digits that has is going to be how many sig digs you should put your answer into. Okay, so as a quick reminder here, any digit that is not 0. So 1, 2, 3, 4, 5, 6, 7, 8, 9. All of those are significant. With zeros, sig digs get a little bit more complicated. So as a reminder, or as a refresher from previous science classes, for zeros, if you have a trailing 0, so a 0 that comes after non-zero digits, those are going to be significant. So this 150 grams, that has 3 sig digs because the 1, 5, and 0 are all significant. Okay. Same with 20 degrees Celsius. The 2, 0, and 0, those are all significant because the zeros are trailing zeros, so they count. So this also has 3 sig digs, and then for our final temperature, that also has 3 sig digs. Okay, so for zeros, trailing zeros count. Zeros in between non-zero digits, so such as this 0, I call them sandwich zeros, they count as significant. Okay, but zeros that are what I call leading zeros, so that would be these zeros, they come in front of a non-zero digit, they do not count as significant. Okay, so that's an important reminder, and you will be expected to know how to count your significant digits and also determine how many sig digs you should have your final answer in. Okay, so with this one, since all 3 of our numbers have 3 sig digs, then the lowest amount of sig digs we can have our answer in is 3 sig digs, so that's what we're going with. Okay, so if I count from the far left, 1, 2, 3, there's my cutoff line. Now the problem here is that 208 is not the same as 20,866.2. Okay, so how can we remedy this? We can fix it using scientific notation. Okay, now let's quickly review scientific notation, and because I don't have a lot of room here, I'm going to have to go back to the previous page. So, scientific notation. I'm going to write a little template here. So scientific notation is typically 1 digit to the left of a decimal, and then you have however many digits you need in order to satisfy sig digs, and then it's going to be times 10 to some exponent. Okay, so let's write down what I just said. Always make sure that there is only 1 digit to the left of the decimal. and that digit cannot be 0. So one digit that isn't 0, so it has to be something 1 through 9 to the left of the decimal. Okay, now let's talk about this exponent. So this e is just a placeholder for the exponent. So let's talk about that. So if your original number, and what I mean by original number, so in this question, it would be this number right here. So the number that is not in scientific notation. So if your original number is bigger than 1, then your exponent is positive. If your original number is between 0 and 1, then your exponent is negative. So for example, if your original number is 0.025, then if we were putting that 0.025 into scientific notation, you would have to have your exponent be a negative number. So that's a quick refresher about scientific notation from previous science classes. All right, so let's apply this here. So once again, how I know that I need to convert this into scientific notation is because 208 is not the same as my value. It's nowhere even close to that 20,866. Okay. Another way that you could know that you need to use scientific notation, if your cutoff line comes ahead of the decimal, you need scientific notation. If your cutoff line comes right on top of the decimal, you do not need scientific notation. And also, if it comes after the decimal, then typically you don't need scientific notation, although you could still use it. All right, so with scientific notation, we only want one digit that's not 0 to the left of our decimal. So let's count how many spots we need to move our decimal. So 1, 2, 3, 4. So I'm going to go 2.0, and now with that 8, I got to look after the cutoff line. So if the number after the cutoff line is 5 or higher, you need to round the number ahead of the cutoff line up. Okay, so that's why I'm going 2.09. And we said times 10 to the power of, so this 4 represents how many spots we moved the decimal. And I'm going to make sure it's a positive 4 because our original number was a lot bigger than 1. Okay. So this is our answer in 3 sigdigs. Now, if you're wondering if you could have written this answer in kilojoules and just avoided scientific notation, yep, you could, because the question didn't specify what units it wanted energy in. So we could have also done 20.9 kilojoules. Okay, so this isn't in scientific notation, so that's why I can have more than one digit before the decimal here. So both of these answers are the same value. They're just in different units here. Now, how I did this for kilojoules, so you got to remember there's 1,000 joules in a kilojoule, so that's what I used for my conversion. I just moved the decimal 3 to the left. All right. Example number 2, a certain mass of tin is cooled from 1200, that should be degrees Celsius, to 850 degrees Celsius, and it releases, so that's a key word there, 1.50 megajoules of energy. What is the mass of tin used? So let's write our list of givens. Okay. So for kinetic energy, I want to talk about that one first so I can talk about this word. So the word release means that this much energy is coming out of the system. So if the system is losing this much energy, I need to write it as negative 1.50 megajoules. Okay. Now for our mass, we have no clue. That's what the question's asking for. For our specific heat capacity, they mentioned we're dealing with tin, so let's look up tin. So tin is right here, so that's 0.227. And then our change in temperature. So the first one that they mention is your initial. The second one that they mention is your final. So we're going final minus initial. So 850 minus 1200. And that's going to give us negative 350 degrees Celsius. Okay, so looking at our list of givens, I'm noticing that energy and this top unit from specific heat capacity, they're not in the same unit, so I need to do some converting. Okay, so for converting megajoules into joules, we want to cancel out megajoules. So since it's in the top, I'm going to put megajoules in the denominator, so that I have the exact same units in the top and the bottom so that they cancel out. I want to be left with joules, so that's what I'm putting in the top. Now for the conversion, you always start with the bigger of the two units, and that's going to be megajoules. Okay. If you're wondering how you should know that megajoules is bigger than joules, what you can do is go to your data booklet. So this is on page 3, just scroll down a little bit or look down, and they mention the prefixes for the metric system here. So they start with the biggest. So tera in this list is the biggest prefix, whereas pico is going to be the smallest prefix that they mention. Okay, so since mega is here, if you're wondering where joules would be, it would be in between here. So joules is one of your base units, and the base units happens between kilo and milli. How you know something is a base unit is typically if the acronym for it is only made up of one letter, it is a base unit. So that'll get you most of the time. That'll get you what you need to know. Okay, so here we're seeing, okay, for 1 megajoule, that's going to be 10 to the power of 6 joules. That's what it's telling us here. So all of these numbers are telling you how many of each of these would be in a base unit. Okay? So 1 megajoule will give us 1 times 10 to the power of 6, which is the same thing as saying 10 to the power of 6. So if I multiply that out, let's clear this. How I do that is negative 1.5 times by 1, and then I'm going to go second function log to get that 10 to the power of 6. Hit the right arrow, close the bracket, hit enter. So that's going to be, how many? It's going to be negative 1,500,000. Okay, so you could write it as that, or you could just write it as negative 1.50 times 10 to the power of 6. And that'll be joules, because megajoules canceled out. All right, let's start off with our formula. So EK is equal to MC delta T. So remember, we're talking about the kinetic energy of tin. We're going to be finding the mass of tin, the specific heat capacity belongs to tin, and the temperature change also belongs to tin. So what I'm saying is remember that every one of these variables deals with the exact same substance here. All right, so EK, that was negative 1.50 times 10 to the power of negative 6. Okay, so what you could do is you could either substitute in all of your numbers first, then rearrange, or you could rearrange your equation first, then substitute in. I like rearranging first. So I want to find mass. So I'm asking myself, okay, what is specific heat capacity and delta T doing to mass? Well, they're multiplying, so I got to do the opposite, which is dividing. Okay, so these cancel out, and I'm left with EK divided by C delta T is equal to M. So this is the formula that we're going to be using here. So I'm going to scooch this up, and I'll flip this equation around, and then I'll plug in my numbers. So negative 1.50 times 10 to the power of 6 divided by, so what was specific heat capacity? 0.227. So this is in joules. Oop. And then change in temperature was negative 350. So looking at this, I've got joules in the top and the bottom. I've got degrees Celsius, top and bottom. So for my mass, we know that our units are going to be in grams. Okay, so let's throw this into our calculator here. So I'm going to put brackets, negative 1.5 times 10, so I went second function log, to the power of 6, hit the right arrow, close the bracket, divided by bracket 0.227 times by negative 350, close the bracket, hit enter, and that's what we get. All right. What was that, 79? Yeah, 7982. Number kept on going on forever. All right, so let's look at the values given to us. So 1200 here, that has 4 sig digs because the zeros are trailing zeros, so they count as well. this has 3 sig-digs in it. And same with this. This has 3 sig-digs as well. So we always go with the least amount of sig-digs, so we need to report this in 3 sig-digs. So I'm going to count from the far left, 1, 2, 3. There's my cutoff line, so it comes in front of the decimal point, so I need to use scientific notation. So I'm going to count 1, 2, 3, 4. So my answer is going to be 1.89 times 10 to the power of positive 4, because my original number was bigger than 1, grams. And that one's done. Let's go on to the next one. So if 20 kilojoules of energy, so that's our EK, is absorbed. Okay, so that's a key word. If something is absorbing energy, it's gaining that energy. So absorbed is the word version of positive. So it's absorbed by a 500 gram piece of aluminum at negative 30 degrees Celsius. What is the final temperature? All right, so let's write out our list of givens. So EK is 20 kilojoules. Okay, so 20 kilojoules, if you want to do a conversion, so kilojoules is on top, I'm going to put it in the bottom so that they cancel out. Kilojoules is bigger than joules. How I know that is I look here, and our base units are here. Kilo is above that, so that's how I know. Anything above the base units, that's going to be bigger than the base units. And in 1 kilo, there's going to be 1 times 10 to the power of 3. In 1 kilojoule, there's going to be 1 times 10 to the power of 3 joules. Okay, so you could either write this as 20, actually, if we wrote it as 20 times 10 to the power of 3, that would not be correct notation for scientific notation, so I'm going to write this as 20,000. So if you want to throw this into your calculator, that's what it's going to be. Ultimately, this tells you here, because you're multiplying by this value, this tells you to move your decimal over 3 spots to the right. Specific heat for aluminum, if we look up that, that is right here, so 0.897. Okay, and we were given our initial temperature. That was 30 degrees. Oh. Or sorry, negative 30 degrees. Okay, how do we know that's our initial temperature? Well, they asked for the final temperature, so that's why it has to be the initial temperature. Okay. So we got our givens figured out. Let's write out our formula. So EK is equal to MC delta T. And what I'm going to do, like, we're looking for final temperature, which is trapped in here. So I'm going to do this a bit stepwise. Let's just isolate delta T. So I asked myself mathematically, okay, what's mass and specific heat doing to delta T? Well, they are multiplying, so I got to do the opposite, which is dividing. And what I do to one side, I need to do to the other. So these cancel out. EK is divided by MC is equal to delta T. Okay. So at this point here, I'm going to leave it for now, but know that I'm going to expand delta T later. Okay, but we're using this for now. So I'm going to switch this around. and let's plug in some numbers. So 20,000 joules for energy. So keep in mind, I mentioned this up here. This is a positive 20,000 because the energy was absorbed. So whatever you do, don't forget about your sign for energy because that can make a big difference. All right, so 20,000, and then that's going to be divided by 500 grams times by specific heat capacity Okay, so what's going on with our units? Grams, those cancel out. Same with joules. So we're left with degrees Celsius. All right. So let's move this up here and let's figure out what all this is. So 20,000 divided by 500 times 0.897. Close the bracket. And that's what we get. So 44.5930 keeps on going on forever. So because the number keeps on going on forever, I'm going to go ... to mean the number keeps on going on forever. However, I'm going to keep the raw number in my calculator for future calculations. Okay, so delta T, I can expand that into final minus initial. So T final minus T initial. Okay, oh, I better put my units there. All right, we know that my initial temperature, we know that that was negative 30 degrees. And that's degrees Celsius. Okay, so negative times a negative is a positive. 44.5930 keeps on going on forever. Okay, so to isolate final temperature, it's being added by the 30, so I'm going to do the opposite, which is subtracting. Final temperature is going to be 14.5930, goes on forever. And that's going to be degrees Celsius. All right, so sig digs. What were we given? So this is in 3 sig digs because the zeros are trailing zeros, so they count. Same with this. It's going to be 3 sig digs. Same with that, 3 sig digs. Okay. So my cutoff line is going to be 1, 2, 3, right there. So since my cutoff line is after the decimal, could we use scientific notation? Yep, but we don't have to. So 14.6 degrees Celsius. And there you have it.